Hello everyone, today's video lecture will be on the if-then-else algorithm and value tables. Previously we did cover the switch case algorithm. The if-then-else algorithm is similar to that, but it has more flexibility. And value tables will allow us to track the values of our variables throughout our code in order to determine if our code is working correctly. So onto the if-then-else algorithm. As I said, it's similar to the switch case algorithm, but it employs ranges instead of discrete values as your discriminating criteria. So instead of having to have an integer number, we can have a range. So with the marks example, instead of having to determine the tens and then displaying only a 9 or an 8, etc., we are able to say, is this variable greater than 90 or less than 99 in order to assign an A+. So we can use ranges instead of discrete values. We're also able to use compound conditions or Boolean sets of several different conditions. So we can use ands and ors and build up pretty complex discriminating criteria for whether a section of code need to be run. There are three forms of the if-then-else algorithm with increasing complexity as well as flexibility. We have the simple if-then, we have if-then-else, and we have if-then-else-if, which is the most general. The basic syntax of the if-then algorithm is simply if followed by your condition. So, for example, if mark is less than 50, then display student fails. End. Remember, for every algorithm we implement, we need to have our keyword to start it, and we need to have an end in order to show Octave that the end of the algorithm is on a certain line, and it can continue after that line once the algorithm has been executed. The if-then statement is used in instances where the code must only be executed for a particular condition, but no action is required for all other states. So we don't have an otherwise, like in the switch case statement. We only worried about if a certain condition is met, run this code. Otherwise, do nothing. It is an abridged version of the if-then-else algorithm. The if-then-else algorithm has similar syntax to the if-then algorithm, with the exception of an else statement being added. This else statement is similar to the otherwise statement in your case statement, where it is executed if the condition is not met. So with an if-then-else, if your condition is met, you run your executable code under that section, and if it is not met, you run the executable code under the else statement. With the final, most general form of this statement, the if-then-else-if, we have, again, a similar syntax where we have if a condition is met, then we run a certain code, but it allows us now to have multiple conditions that we can check for, and not just a single condition and an else. So here we have, if condition 1 is met, run this code. Else if condition 2 is met, run another set of code. Else if condition 3, and so on and so forth. You can have as many else if statements as you want, but then you do need to have an else clause, where if none of the above conditions are met, the else is executed. We have a similar thing happening here to the switch case statement, where only the first condition that is met is executed, and then the program will move to the end of your if-then-else if statement. So you cannot have multiple conditions being met at once, and you cannot have multiple sections of code under multiple conditions being run. So we can think of the if-then-else-if as a chain of if-then-else algorithms, which is similar to a switch case with using data ranges and complex discriminating conditions instead of comparing only to discrete values. We can have as many else ifs as required. And if any condition is met, the associated executable code is run and the program continues after the end statement, but only the first condition to be met will be executed. If multiple conditions should be met, the subsequent conditions won't run. Okay, so we're going to move into a little bit of Workspace Practice. So you can open up Octave. You're going to create a new script file. I've already created the new file, and we're then going to save that file. as markmaker. We are then going to type in the code on the screen. So we're going to say test is equal to floor. Remember, the floor function rounds a number down. And we're going to say 100 scalar multiplication or element-wise multiplication by rand, the random function, where we're going to create a 1 by 1 vector, which is essentially a scalar value. Remember, in Octave, everything is seen as a matrix. So we're creating a 1 by 1 matrix or a scalar random value, in this case between 0 and 100. Because the random function generates values between 0 and 1, if we multiply 100, we get values between 0 and 100. And we're rounding this down. We're then going to say if. Okay, so we're starting our if statement here. You'll note that the word if turns blue, okay, to indicate that we have opened an algorithm within Octave. If we type a capital I, remember, it has recognized it, but it's going to give you an error. It needs to be a lowercase I. Everything in Octave is case sensitive. So we have if test, the variable we've just created on the line above, is less than 50. We're going to take some action. In this case, we are going to display marks aren't looking too good there. Okay, so on this section of code, we'll notice that on this particular section of code, we have that marks aren't is highlighted in orange, which means that Octave is picking it up as text, and the rest isn't, and then we have an unclosed quotation mark. The reason here is that the program is seeing a single quotation mark followed by a closing single quotation mark and saying that that is text. However, the rest of it isn't picked up. So if we do have text that has apostrophes in it, we need to use double quotation marks to open and close the text, and our single quotation mark within the text indicating an apostrophe. And there you'll see that now the entire sentence is highlighted in orange, so Octave has picked up that entire sentence as text. We can then end our if statement. I'll then just save the code. If we run the code, we can see that we get a message depending on the value of the variable test. Within our workspace, we can see the value that test was assigned. Now remember, every time we run this code, test is going to be assigned a different value because we've randomized test. So if we run it again, test is now 35. It's still less than 50 though, so we're getting our message. If we keep running it and we get to a value higher than 50, in this case test is 69, we don't have anything displayed by the code. So we have the statement of code run if the condition is met, and if it's not met, nothing happens. If we now unsuppress the value of test, so removing the semicolon from the end of that line, every time we run the code, we'll be able to see the value of test. We need to save the code in order for that change to take place. We see then test is 77, so we have no message displayed. Test is 98, no message is displayed. Test is 33, we get our message displayed. Okay, so previously we ran the code, we suppressed the output for the variable test, and when we removed the suppressed output, we could see the value of test each time, or it displayed the value of test each time. In general, we will leave the semicolons after variables that have been declared unless we specifically want to see that output. Okay, so the value of test, when it's less than 50, all the lines of code get run, everything including inside the if statement. However, if test is greater than or equal to 50, everything inside that if statement is skipped and not run. So if the condition is not met, the code inside is skipped and we move to the end statement and carry on with any code after the end statement. So if we now look at another example where we create another new script file and we save it as absolute and enter the code on the screen. So now we have if value is less than 0, we can say that answer is equal to negative value. Else answer is equal to value. So in this case, we are taking a positive or a negative number and we are turning it into a positive number, otherwise known as taking the absolute value of the number. If we then suppress the output of answer in each of those steps and we then display it at the end of the if statement. So now we'll save it and let's have a look at how the program runs. Remember, if we just try and run it now, so if we just try and type absolute, we're going to get an error because the value is not defined. So now we need to create a value. So we say value is equal to, in this case, I'm just going to say 5. As soon as we do that, we can see that there is value 5 stored inside the workspace. We still have test from running the last code because we didn't clear the variables. So we have value there. And if I just adjust these column widths, we can see that value is 5. If we then try and run absolute, we can see that it'll make answer equal to 5. The variable value remains in the workspace after running the script, the same as the variable test remains in the workspace after running the script. Unless you explicitly clear the variables, they will remain in the workspace even running subsequent scripts. So in general, you want to clear the variables that you don't need after running the script, otherwise you end up with a massive amount of variables in your workspace that you don't need. This can be problematic when you end up with variables containing very large matrices. So if we have a value less than 0, so for argument's sake we have value is equal to negative 5, and we then run our code, what's going to happen is we look at the first if statement, it's true, then runs the code under that if statement, and then it skips to end. We skip everything in the else clause. So if value is less than 0, value is negative 5, it is less than 0, we move into the next line, answer is equal to negative value. So answer is equal to the negative of negative 5, so our answer will be 5. And then nothing more is run after that. Remember that we skip to the end, and we then run the line answer, which prints the value answer, or the value of answer. If the value is more than 0, like before, so I'm just going to put value back equal to 5, then the second set of commands is executed. So in this case, value is 5. So if value is less than 0, it's false. We don't run the code under that statement. We move straight to else. Answer equals value. So our answer is now equal to 5. And then we hit end. So if we run absolute again, we get answer equals 5. We just clear everything as well as clear the variables. Say value is equal to 5 again. And then run absolute, it's 5. If we change the value of value, so we make it 10, the program will still run as expected. We try negative 10, Okay, so it'll run for any value that we can store within value. That is the power of using variables instead of absolute numbers. We can use that code for any different input case. So if we now go onto Sakai and open the code called mark decision, you can download it from Sakai, it will be uploaded. I'm just going to open it here from my directory. We have the following code on the screen. So this script is looking at a student's mark and it's deciding based on whether it's greater than 50, less than 50, or equal to 49. So if we have a look at the code, we have line 1, if mark is greater than 50 and mod of mark by 10 is equal to 9. So now we have a compound condition or a complex discriminator here. Both of these conditions need to be true in order for the code to run. So it's asking, first of all, is the mark greater than 50? And second of all, is the mod of the mark by 10? So if we divide the mark by 10 and look at the remainder, if that is 9, so if the value of the mark in the unit section is 9, do we add 1%? So do we round a 59 to a 60? Do we round a 69 to a 70? Then the next statement, if the mark is equal to 49, we need to decide should the student pass, should they not pass. And if the mark is less than 49, the student fails. Otherwise, for any other condition, so any condition that's greater than 50 and doesn't have a 9 in the units column, the student just passes. So if we look at the example here, where we set mark is equal to 59, and we then run mark decision. What gets printed to the screen is maybe add 1%. Just a quick note, if we have our text like this, we get it stored in the answer variable and then displayed. If we use the display function, the text will just be displayed without being assigned to the answer variable. So that just depends on what you want your output to be, how you want it to work. Using display can be cleaner. Okay, so if we then just have a look at what happened when that code ran, we checked, is the mark greater than 50? Yes, because 59 is greater than 50. Then mod of 59 by 10 is 9, okay, because it's essentially 5, 9, and the remainder there is 9. So then we run the line of code beneath that statement. We skip over everything else within that else if statement, and we go to end. So now if we try it with a mark of 49, so we can change the variable here to mark equals 49, and we run mark decision. Okay, so it gives us a few warnings, which we don't need to worry about. I'll explain that now, but the answer that it gives us is maybe let them pass. Okay, we'll get to the warnings now. Let's just have a look at what happened with the code. So we checked, is mark greater than 50? No. Okay, so part of our condition has already been violated, so this entire statement cannot be true, even though the second part is true. Because of the and, if one of them is false, we skip the code underneath there. We move to the next if statement. Else if mark equals 49. Remember, the double equal sign is for comparison, a single equal sign is for assignment. In this case, yes, the mark is equal to 49, so we run the code under this condition, and we skip all the other code and move to end, which is exactly what happened, and we ended up with maybe let them pass being printed. Now onto these warnings. It just says warning, MATLAB style short circuit operation performed. Okay, so all that's saying is that you've used this shortcut, which is recognized primarily in MATLAB. It won't affect the running of your code. So in general, if you see warnings, you don't need to worry, but if you see errors, there's something wrong. So now we'll look at a mark of 47. If we then run our mark decision, say that the student has failed. If we have a look at what happened in the code, our first condition now is false on both counts. Our second condition is also false. So we skip the code under the conditions that aren't met. Our else if, is it less than 49? Yes. So we run the code there, and then we skip the else clause and move to end. The last example, if we look at, let me just clear the screen. If we look at mark is equal to 51, and we then run our code, we're going to just get that the student passes. Okay, so the first condition is false, the second condition is false, the third condition is false. So we run our else statement because all the conditions before that were false. And then we move to end. So just remember that only the code under the condition that is true is run, and then the algorithm immediately moves to the end statement. We can only have one true value. So now moving on to value tables. Okay, so value tables are a useful way to test your flowchart or your code in order to see how your values change at each line or at each stage, in order to track where you may or may not have made a mistake within your code. A value table will include columns for all the variables in the program. So every variable you have will have its own column where you'll track its value through each line of your code or each line of your flowchart. You need to have columns as well for every question that is asked. So every time you have a discriminator, so where you have an if statement, where you have a case statement, every time you have a discriminator in your flowchart, you need a column for that question so you can keep track of when that discriminator is yes or no, or true or false. And lastly, you need a column for screen output. So every time you output something to the screen, you'll record it in your final column of your value table. The values of your variables will never change from one row to the next unless there's an action in the program. So remember that a variable will always keep its value unless the program specifically says it needs to change. Same thing in your value table. The variable's values stay the same unless there's a specific action within the code or within the flowchart that causes the variable value to change. Any changes in variable value should be highlighted, okay, in order to make it easy to see the patterns in the program and to see what's changing where. And question and screen output columns will only be written in the line where they are done. So your variable values you track throughout your code. Every single line you'll have a value even if it hasn't changed, and you'll just highlight the changes. But where you have questions and screen output, we only show the values or the outputs for those columns on the lines where they happen. Okay, we'll explain this in an example. So we're going to look at the Fibonacci sequence, where each term is the sum of the last two. Okay, so we have the first two terms being 1, we add those together to get our next term 2, we add 1 and 2 to get our next term 3, we add 2 and 3 to get our next term 5, and so on and so forth. The first step is to write a program that will work out the third term and we'll make a value table in Microsoft Excel. I've made one already, it's now on the screen. We can see that we've included columns for each of our variables and for our screen output. We can download this Excel file from Sakai. So if we look at the code that we can use in order to calculate the third term of the Fibonacci sequence, okay, so this is only going to be for the third term. The lines are as follows: Fib1 equals 1. So if we follow that along, if we look at our first line of code, it says Fib1 equals 1. So we track that in our value table. So we have a value of 1 there and nothing else. We then move on to line 2. Fib2 is now 1, but Fib1 is still equal to 1. So it still has a value of 1, so we record it in that line. I'm just going to then change Fib2 is now also 1, and we don't have a Fib3 value yet, we don't have a screen output. We need to highlight the changes. So if we move then onto line 3, we have display Fib1. So we're going to have the values staying the same. We still don't have a variable value for Fib3, but now we have screen output. Our screen output is going to be Fib1, so it's just a 1 in this case. If we then move on to line 4 is just display Fib2. So we have, again, the value's not changing. We still don't have 3, but we have a screen output here, and we're displaying Fib2. Okay, we're only displaying Fib2 on this line, and we're only displaying Fib1 on that line. The next line calculates the value of Fib3, so it's 1 plus 2, or Fib1 rather, plus Fib2. We then have the values of our first two variables we've created still remaining unchanged, and we have Fib3 is equal to 2. Okay, so there we have a change in variable value. We can highlight it. And we have no screen output once again. We now are swapping our variables in order to calculate the next term. So Fib1 now becomes Fib2. So that's a 1. Fib2 now becomes Fib3. So that becomes 2. Sorry. We're doing it line by line. So Fib1 becomes Fib2. So that's a 1. That stays 1. We're going to highlight this here because even though the value strictly hasn't changed, we have assigned it a new value. But in this case, the new value is the same as the old value. Fib2 stays the same. Remember, we're looking at this line over here. Fib1 equals Fib2. Fib3 is still equal to 2, and we have no screen output. We then move on to the next line. Fib2 equals Fib3. We have Fib1 stays the same. Fib2 now becomes 2 because it gets assigned the value of Fib3. There's a change in variable value there, so we'll highlight it. Fib3 remains 2, and we have no screen output. We then, in the next line, display the value of Fib2. So the values of our variables stay the same, and we have screen output of Fib2, which in this case is 2. And the last line says clear Fib3, so we have 1, 2, 3 gets cleared, and we have no screen output. And we highlight the fact that Fib3 got cleared. So now we're essentially ready to repeat this segment of code in order to calculate Fib4, and we can then repeat it in a loop. So I would like you now, before Monday's lecture, to try and implement this code in a loop to display or implement a flowchart for displaying as many values in the Fibonacci sequence as possible using a loop. We'll run over loops in the next lecture within Octave, but first try and produce the flowchart. So in review, we looked at the if-then-else algorithm, which is a branching algorithm similar to the switch case algorithm, but it's based on ranges of values and complex combinations of Boolean conditions instead of comparing to discrete values. We also looked at value tables, which test the behavior of a flowchart or a program and do exactly what the program says. Okay, so on every line of your value table, you're tracking exactly what that line of code or that line of your flowchart has done, and you're tracking the value of the variables. You have columns for every variable, as well as for all your decisions and your screen output.